thanks for introduction. And yeah, it's my pleasure to give a talk here. So yeah, so I think can we get started? Yes. Okay. So probably we can get started.
Oh yeah.
Oh, we should wait. Or
you can start when you're ready.
oh, okay. Okay. Thanks for introductions. Okay. Yes. Again, it's my pleasure to give a talk at the at Grass Lab. Yeah. I'm Zhongyu from Berkeley. So I'm going to discuss a very interesting question today. Is that how can we, or whether we can bridge the model-based control and the model-free reinforcement learning on the leg robots. So a brief introduction of myself. I'm a fourth-year PhD in mechanical engineering, and I did my undergrad in China. I actually spent a year in Pennsylvania, but another side where I was doing research internship with Professor Ralph Hollis at CMU. I did I work with a ball board, which is a robot that is balancing on a ball. And then I moved to California to do PhD with Professor Koshio Swinas. So I mainly focus on the leg robots. So I'm interested in how to develop a robust and versatile locomotion controllers for this kind of robots in the real life, not only for the biped, but also for quadrupeds. I'm also interested in how to enable this kind of robot to autonomously and safely navigate through an unknown environment, but also clustered environments. I'm also interested in how to enable this kind of robot to better interact with humans as well as other robots. So first questions, why do we need the leg robots? Since human environments are designed for legs, leg robots can better coexist with our human beings. Actually, the second reason is quite straightforward, is that leg locomotion is a very hard problem, so we need to solve it. So why is the leg locomotion hard? So let's take Cassie as an example. So this is a Cassie robot. Is a biped robot. When it's in about 1 meter height, when it's fully standing. So you have 2 legs for sure, and each leg have 5 actuating motors and 2 passive joints connected by the leaf springs. So you have 20 degrees of freedom in total. It's a nonlinear system. It's a hybrid because when it starts to walk, and it's under actuated systems because of the existence of the springs. If we write down these 4 order dynamics, we can actually obtain this line of equations. The left-hand side contains the robot mass, the states, the robot mass matrix, and some other terms such as gravitation, Coriolis. The right-hand side is the input, which contains the motor torque, spring torques, as well as the ground reaction force. So does it look simple, just one line of equations? But if we write down all the details of these equations for Cassie, we will obtain a huge file. And this actually requires about 2.6 megabytes of SQL to store this kind of dynamic equations. So such high dimensionality and high nonlinearity, making tackle the problems on Cassie, on this kind of robots, become very challenging. So how to solve it? We can use the model-based optimal control framework. We can still use the full order model, but only utilize it offline. And then we can also come up with some reduced model, which is a simplified model to approximate the robot dynamics. And in this way, we can make it online, optimization online. So the good thing is that we can actually apply stability and safety guarantee on the models we just developed for the robots. But the drawback of this method is that we always need to look for good models. Okay. We can also look at another regime, which is the model-free reinforcement learning method, where we don't use models to develop controllers, our control policy, but instead we train our agent, our robot, through trial and errors. Actually, we will see that using this method, we can actually obtain quite robust and agile maneuvers in the real world. But the price is that we lose the ability to provide any kind of guarantee, such as stability or safety. So can we actually combine the advantages from both sides? So this is kind of sneak preview, but we will see that when we consider the robot controlled by its IO policy, we are able to explicitly find a linear model to describe this closed dynamics. And therefore, we can apply the safety critical we can apply the model-based method to provide some safety guarantee on top of this linear system. So this will be the main topic today, but I will also briefly introduce both sides as some backgrounds. Okay, so the first part, how can we use model in the leg robots? So as I mentioned, we can still use the full order model of the robots just using the equation I just demonstrated, but only utilize it to trajectorizations offline. And online, we can just come up with some simple controller to check this kind of optimized trajectories. We can also extend the similar method to a quadruped robots, by which we can enable a robot to perform jumping maneuvers like in the real world. We can also come up with some simplified model to approximate robot dynamics, and then we can utilize this online. So let's take the collision avoidance as examples. So in this work, we come up with a reduced model, which namely spring-loaded inverted pendulum slip to approximate the Cassie's working dynamics. And this model is utilized in trajectorization online to enable a robot to avoid obstacles nearby. And if there is a high constraint environment, the robot can crouch down and travel underneath that, and then recover to a normal walking height. So please know that everything here running online. There's no preview map. The robot knows nothing before being given a goal locations. So basically, using this kind of a method, we can actually enable robot to autonomously and safely explore unknown and crowded environments. So we can also mitigating the obstacle avoidance by introducing hybrid mode switchings. So in this case, we let the quadruped robot to lead a blindfolded person by a leash. So the leash can be either slack or taut. So basically, when the robot enters a very narrow space, the robot can let leash go slack, and then there's no force on the guiding leash, so the blindfolded person will stop, and then the robot can reposition and reorient, find a better configuration to pass through this narrow space, and then make the leash go taut again, and the human will follow with the robots. We also introduce similar ideas on the multiple quadruped robots to collaboratively using cables to tow a heavy load. So basically, when this kind of a team of robots enter a narrow space, some of the robots will let the leash go slack and squeeze into this kind of a space, and then make the leash go taut again. So, but in all of this kind of method, we actually decoupled the obstacle avoidance problem with the locomotion control, because the models used in the trajectorization for the collision avoidance is different from the models we use for the locomotion control layers. For example, in the quadruped case, we're just using a double integrator to describe the robot dynamics in the obstacle avoidance in order to mitigate the complexity bring up by the hybrid mode switching, which could be mixed integer problems in the optimizations. So most recently, we also coupled the most obstacle avoidance in the locomotion controls. So we call this a safety critical locomotion control, because the safety will directly apply a safety guarantee on the locomotion control layer, which is the MPC, for the centroid model for the locomotions. So in here, we apply the control barrier functions on the MPC layers. So we show that the robot using this kind of method can actually safely travel in a very tight space, and everything is also online. So the cool things behind this experiment is that right now we are able to represent both the robot and the shape of the robot and obstacles as a convex polytopes. So compared to commonly used spherical approximation, we usually over-approximate the robot shape. We now can have a finer representations of the shape of the robot and the obstacles. So this kind of research, this kind of experiments is only possible till the recent breakthrough of the control barrier function series. For example, CBF, the control barrier function, is a constraint, and it may violate with the input of the system. So how can we ensure there is a feasible solutions when we apply the CBF online on the robots? So how to combine the CBF with the model predicted control MPC, and how to consider the polytop, the obstacle avoidance with polytop in using CBF. So this line of research is mainly done by my colleagues Jun and Akshay. So if you're interested, I highly recommend you to look at their papers. So this kind of a cool demo experiments, which I just grabbed the series from their papers to use, and it actually works very well in the experiments. Okay, so actually to wrap up, the models can do lots of things. We can use full the models offline, and we can also use the simple model online. So what is the drawback of this method? So first of all, it requires extensive parameter tuning on the robots. So we need to retune the control gains on our Cassie robot from time to time. If we directly deploy the controllers on other Cassie robots, such as the Cassie robot at Penn or the Cassie at Michigan, so that parameters should be retuned. If we're adding additional load, we also need to do retune. So I think all of this is because there is a huge modeling errors. There's also things we cannot model well, such as the model agents. Secondly, different robots may need different models. So we do everything. We build up entire pipeline for Cassie using the models, controls, navigation, everything. But if we want to switch to a humanoid robot digit, everything should be restart from scratch. So what about the mini cheetah, which is a quadruped robots? What about other different kind of quadruped robots with different morphologies? So can we make our controller don't rely on the models? So this comes to the second part of my talk, which will be, how to use model-free IA on the Lego robots. So let's take, Cassie as examples. So this is our robot. So right now, the control policy is no longer rely on the models, but it's represented by a deep neural net. So in this case, we are using a multi-layer perceptions. It directly outputs the 10-dimensional joint positions, which is design joint position for the robots. After passing through a low-pass filter, it will be utilized in a joint level PD controllers, which run at a higher frequency to generate motor torques on the robots. The input of the policy has 4 parts. The first is the reference motion. We actually have a bunch of optimized, gates for Cassie, conditioned on different walking velocity and walking height. The second part is the desired walking velocity and walking height, as well as the turning yaw rate. So please know that this turning yaw rate is not the reference motion doesn't include the information about turning yaw. Okay. And the third part is the robot current state feedback, as well as a short history, namely 4-time step history of the robot state feedbacks. The fourth part is a short history of the policy's past output. So by combining the input-output, the history of the input-output of the robot, we can actually enable the policy to implicitly encode the dynamics we are controlling with. So this policy runs our policy runs at 30 Hertz, and the rest of the parts will run at 2K Hertz. Okay, so we optimize this policy, which is a deep neural net, by reinforcement learning. So at each time step, the agent, which is our robot, take from the current observations and take actions inferred by the policy, go to the next stage, and then it will receive a reward. Our objective of IA is to maximize the total reward along the trajectory using the policy. Okay, so our reward at each time step is defined to encourage the agent to mimic the reference motions, as well as minimizing the tracking errors and impact force, and to be energy efficient. So we train our policy, our agent, in a simulations, which is the Madrigal's. But in order to mitigate the large sim-to-real gap, the gap between the simulation and the real world, we extensively randomize the dynamics parameters in the simulations. For example, we randomize the joint damping ratio, link mass, and the link center of mass offsets, as well as the ground friction ratios. So we also simulate the sensor noise and communication delays. So after this policy is trained in the Madrigal, we test it or validate it on high fidelity simulators, which is the MATLAB Simulink. And after this is validated, we can directly deploy it on the hardware in the real world. So our policy is able to directly transfer to the robots without any tuning on the hardware. So this is actually the first experiments we deployed IO policy on the robots. So the policy shows kind of reasonably good ability to enable robot to check different velocities in the real world, such as walking to different directions, forward, lateral, using a single policy and changing the walking height, and also working with different velocities like at different walking heights, but you're just using a single policy. And it can also recover to a normal height. It can also enable robot to do a turning. So please know that, as I mentioned, the turning motion is not included in the reference motion. We basically encourage the agent to infer the motion that's outside of the reference motion. We also do some outdoor experiments. So there is a thing that the robot do a turning first and then do a faster walking gait. And not as fast, but kind of fast gait. So, but these policies, the biggest advantage of this kind of policy is that it shows quite good robustness on the hardware. So this such control policy is able to maintain the gait stability from a random perturbations from outside. So you can see in this scenario, the robot takes a sleep on the gantries, but the control doesn't blow up, and the robot can recover to the backwards gaze afterwards. And there's another bigger sleep. So this is my previous segment where the robot almost fall down, but the control doesn't blow up. Instead, it used the safety leash to regulate the robot back to a regular walking gait. So it's very like our humans, like when we almost fall down, like take a sleep and almost fall down, and some person besides us, give us a hand and pull out up. Okay, so this is like robust into the change of the frictions, and we also apply some unknown load on top of the robots, and robots can also drag the gantry without anyone pushing it, and follow and with the carry the load. So this is for biped controls. We also extend the similar techniques on the quadruped robots. But in this case, we are thinking about one question: is that there is a kind of a recent search of the lots of commercially available quadruped robots in the real world, and lots of robots have different designs, but they're actually seemingly converging to a very similar morphological template. So the question is, can we have a single controllers for different kind of quadruped robots? So this is the method we propose. So this policy is represented by a deep neural net, and it directly output jump positions. But this policy requires very simple observations. It only has 3 parts. The first part is a scalar from 0 to 1, indicating the phase of the gait. The second and the fourth parts are just a short history of the past, the robot space feedback and policy output, and then that's it. But unlike commonly, used IA, which with a fixed agent, during training we procedurally randomize the robot morphologies. So by doing this, we are able to generalize the learned locomotion skills on different kind of quadruped robots with different morphologies. So we actually showed yeah.
A question over here. Hi, nice job on presentation so far. I wonder on the previous slide, like the Cassie example, do you have like a comparison between the optimal control way and the way you're doing with the walking, and like the performance, some kind of performance metric comparing the two?
Yeah, I have a kind of metric. Yeah, I have a metric, but do you want to see it? Probably you can. I can. Let me see whether I can find it. Yeah, something like that. Yeah, it's kind of comparisons between the IO. So these are kind of backup slides basically. But yeah, so it's like a very good question. Thanks. So it's more like this is comparisons between IO policy and the the model-based method we developed beforehand. These are the examples where the robot shows very fast walking gait by the IO policy, but using the previous model-based method, robot directly fall downs. So this is one examples, but we actually extensively test an entire range of the possible commands as the at this side. So the blue dot are the feasible commands that where the IO policy can maintain a stable gait on the robot to check the desired command, which has the desired forward walking velocity, lateral walking velocity, as well as walking height. And the blue one is basically controlled by the HZD. So basically, you will show that our IO method can actually cover 4 times larger of these kind of feasible commands and the feasible than the model-based method. Yeah.
Oh, thank you.
Right. Thanks for the question. Let me go back to the Quadrupeds parts. So yeah, we actually show that I think by just using this method, we can just generalize our locomotion skills on different robots, and we can show that it can directly zero-shot transfer to the single policy, can directly zero-shot transfer to different kind of robots in the most commercially available Quadrupeds robots, ranging from a very tiny robot to a very big robot, such as the Spot. The policy can also generalize to the animal series robot, which is kind of have an inverted knee design compared to the morphological template we used during training. We also show that the single policy can directly deploy on different kind of robots in the hardware, such as A1, the mini cheetah, which are small robots, and the series robot, which is big robots. So we actually open source all the codes as well as the pre-trained policies. You can find this in this link. So basically, the concept behind this idea is that when there is a new robot, new Quadruped robots developed, like people can just download our pre-trained policy and they use this as a baseline controllers to make a pass on their baseline on their kind of hardwares without worrying about building up a new controllers from scratch. So this is right now. This is all about low-level controls for the locomotions for the leg robots. So how about motion planning? So we are thinking about a very interesting question. That is, how can we enable the Quadruped robots to precisely shoot a soccer ball to a random target? So this is actually very interesting because in this case, we can consider robot leg as a robot manipulators. So in this case, actually, we can combine the locomotion and the manipulation together. So this is how we do it. We firstly develop a low-level locomotion, low-level control policies to enable the robot to check arbitrary end-effector trajectories. So right now, the end-effector is the robot toes, and the trajectory is parameterized by the Bezier curve. So the Bezier parameters is an input to the control policies. And during training, we randomize the Bezier curve and encourage the agent to use this end-effector, the toes, to check the reconstructed, the Bezier curve. And we can first, with some domain randomizations, we can actually obtain quite robust controllers on the hardware to enable robot to check, the desired trajectories while maintaining the motion stability, even with some external perturbations. So after this controller is developed and tested extensively on the hardware, we can reuse this policy to train a high-level planning policy to decide which kind of a trajectory we want to perform on the robots by looking at the given goal locations and the detected ball positions, as well as some robot state feedback. So we can also train this planning policy in the simulation and directly deploy it in the real world, but they show a very poor performance, the shooting accuracies in the real world, because there is a huge gap between simulation and the real world, including such as the ball is deformable objects, and the loading dynamics on the ground is actually very hard to model in simulations. So in order to mitigate this, we keep training our planning policy in the real world by just letting the robot to play with the real soccer ball on the real ground, by itself, and collecting lots of kind of real life data, and use this to optimize the planning policy. And after just about 130 shots, the accuracy can be boosted to about 80%. So everything here, each component is trained by the model-free IO, but we can actually find their counterparts in the traditional model-based method. So the controller is basically end-effector tracking controllers for robot arm usually, but in our case, we need to consider about motion stability when we apply this on the quadrupeds. The planner is actually doing a very similar rule as the trajectory optimizations with direct collocation method. Okay, so to wrap up, compared to the model-based method, which requires careful design with expertise, the model-free method can actually automate the design process for the controls of different kind of robots. So currently we are developing a code base that we just need to replace the robot URDF, the robot model files, and the reference motion, and click run. We can obtain a controllers that can work on the hardwares, and we will open source this kind of code base soon. So what's the drawback of this method? So actually, the thing is that right now everything is a black box to us. Neural net is a black box. The robot dynamics is actually a total mess for us. So for the students doing experiments, they probably need to pray to get this to work on the hardware. And the professors in control probably may challenge this kind of method because you cannot show you stability of these kind of controllers. So the underlying reason behind this is that there's no clue about when this method will work and when this method will not work. So can we apply the stability and safety analysis on a model-free IO policy? So here comes the third part of my talk, which that is how to bridge the model-based safety and the model-free IO on the lag robots. So let's revisit the IO controller for Cassie. So this is a closed-loop system, but if we consider the entire thing as a black box, you have an input, which is a 4-dimension, which is the desired saturated working velocity, saturated working speed Vx, lateral working speed Vy, working height Z, and turning your rate theta. The output of this black box is the robot actual working velocity and working height. So the question is, can we find an explicit model to describe this closed-loop dynamics? So why is it useful to doing this? If we can do this, the closed-loop system will become a new open-loop system with the input as commands and the robot actual working speed and the working velocity and working height as output. In this way, we can actually apply some stability analysis on this open loop system, and therefore we can embed this open loop system in a higher level model-based controllers to provide some safety guarantee on the safety critical tasks, such as robot Cassie navigating in unknown environment, unclouded environments. So this sounds very compelling, but is that possible? Thinking about right now, the controller is a deep neural net, which is a high-dimensional nonlinear system, and the robot now is a Cassie, which is another high-dimensional nonlinear dynamic systems. So a nonlinear system controlled by a nonlinear neural network will analyzing the closed-loop dynamics easy. So actually, we find out that these all dimensions, which is the desired working velocity, working height, and turning your rate, are approximately linear. And these all dimensions actually decoupled from each other. We actually validate these 2 points across different IO policies, and these 2 points are only validated under an input within a low frequency range. So notice that all the result here we demoed is obtained on a MATLAB Simulink, which is a high fidelity simulators. So during the training, we train our policy in the Majuko, which don't have any access to the data in the Simulink. Okay, so actually the method is quite straightforward. We're just using the system identification method by looking at the input-output pairs of the system. So let's take the desired saturated working speed as examples. So this is the input. It contains the step input, ramp input, and the chop signal, which is the swipe frequency sine wave. And we can actually measure the robot actual saturated working speed. So basically, the robot controlled by different policies may have different behaviors, but we can always look at the robot step response, ramp response, and the frequency response. Okay, so let's take a look at how this kind of fitting identifications how this kind of identification works. So this is the examples in the saturated walking speed dimensions. So the red one is the input, the black one is the robot actual saturated walking speed, and the blue one is a predicted result using this fitted linear model. We can actually show that just using 3 poles and 2 zeros, we can actually have a quite good prediction accuracy of this kind of input-output pairs. Similar things happen in the other dimensions, such as the lateral walking velocity, walking speed, walking height, as well as the turning yaw rate. We find out that our linear model is good enough to describe the closed-loop dynamics in each dimension. Since we can obtain explicit models, we can actually apply some stability analysis on it. We just find out that not only in the zeros, but or just find out that all the zero and the pools are on the left-hand plane, which means that each dimension is not only asymptotically stable, but also minimum phase. This can actually give us some insights about this kind of robustness of this kind of controllers. Where does this kind of robustness of controllers coming from when we apply this on the hardware in the real world? So this is only a single policy. We'll actually cross-validate this among different kind of control IO policies. So let's take lateral walking speed as examples. So the policy 1 is trained using reward 1 and the training from scratch. Policy 2 is the one we change the reward, but we keep training it using the policy 1. But we just stop it in the middle of the training. It's not well trained. Policy 3 is the one we keep training the policy 2, but train till convergence. Policy 4 is another policy training from scratch with different reward formulations. We actually find out that the linearity actually exists among all of these kind of policies, except this one. You can just use eyeball test. You can tell the nonlinearity still exists. Not even we force to fit a linear models. So the linearity analysis can be actually a potential metric for the convergence of IO, because the reason is very simple. This policy 2 is not well trained. It's only haven't seen lots of samples. Secondly, we also find this kind of cutoff frequency, which is 0.6 hertz, denoted by this kind of red dashed line. So we observe that when the input exceed this kind of the frequency of the input exceed this kind of frequencies, the linearity is not that well preserved. So this can be actually a guidance for the control design. So recall that our system is a 4-dimensional input, 4-dimensional output, which is a multiple input and multiple output systems. We actually show that all dimensions are decoupled from each other under a low frequency input. So this is actually a very, very surprise to us. So why is that? So if we recall that the robot, the previous if you remember, the full order dynamics of Cassie is a huge file. It's a high-dimensional, high nonlinear system. But using the IO policies, the closed-loop system become a linear and a stable system. It also decouples the minimum phase, but most importantly, the robot, the Cassie controlled by its IO policy, a well-trained IO policy, can be now considered as a linear and a stable policy. So this is quite amazing. But did we see this before? We actually, in the traditional model-based method, in the nonlinear control theory method, there is a method called feedback linearizations, where people handcrafted the input-output linearization module to cancel out the nonlinearity of the system. And then on top of it, people can apply the linear feedback controls on top of it. So there's a bold hypothesis is that possible? A model-free IO just learns the IO linearization unconsciously. So why I emphasize unconsciousness? Because we didn't embed a linear structure during the training, such as model-based IO, nor we encourage the agent to behave like a linear system. We just, just let the robot to check different commands, and the turn out to be, could be a linear system. But there are also things we cannot answer, such as, probably not general to all nonlinear systems, not general to all IO tasks, and why does happen, we don't know. It's actually a very interesting and open theory questions we want to bring up to the community. But before solving these theory questions, we can actually apply this in a safety critical task for Cassie. So let's revisit Cassie navigation scenarios. So in this case, Right now we are using the IO policy as a control or as a low-level locomotion controllers, and now the entire closed system become a linear system, and we can identify this and utilize this in a higher level safety critical control framework, namely the MPC with control barrier functions, to enable robot to avoid obstacles, to apply some safety guarantees. We actually have the low pass filters between these two modules because we don't want the input excite the nonlinearity of this closed loop system. Okay, let's take a look at how this looks like. So we simulate our robot dynamics in a high fidelity simulators, which is a meta simulink. The robot vision is simulated in the gazebos, and all the planning data are visualized in RVs. So once given a go locations, there is a global path, and then the MPC is utilized to track this global path, and the CBF is used to enable robot to avoid the obstacles nearby. And when there are high constraint, robot will crouch down and travel underneath. And please know that the controller right now is using an IO policy. And after travel underneath through this scenario, robot can quickly go to the the target locations and lift its body up. So everything running here is online, and it shows that we can actually finish the same trial 2 times faster than the previous model-based method, because IO policy is much more agile and more robust. Okay, so here come to the conclusions. We see that the model-based optimal control framework can do lots of things. We can use the forward models offline, or we can use the reduced model online to to apply some to do some online optimizations. But the good thing is that we can apply some stability and safety guarantee on this kind of on the models we used to develop this kind of controllers. But the thing is that we need to find a very good models for this. We also look at another region, which is another domain, which is the model-free area, where we don't use models, but we actually we train our agent through trial and error to obtain very good and very elegant and robust maneuvers in the real world. But the price is that we lose the ability to apply any kind of guarantee on these kind of systems. So we show that if we consider the robot controlled by its IO policy, the closed system now can become a linear system. We can actually potentially find the linear system on top of it, and then we can utilize this linear system on the model-based control framework to apply some stability safety guarantee on this. So this actually can combine advantages from two sides. IO method is good at controlling high order nonlinearity by leveraging the robot forward dynamics. The model-based method can provide us some safety guarantee on this, and it's more released online because we can actually find a linear model. So here's just the conclusion of my talk. And yeah, I would like to thank my advisor and all of my collaborators. Without them, my talk, this talk will not be possible. And yeah, at last I want to show some interesting videos where our robot fails, and where I break the where I broke the robots. And yeah, thanks, and happy to take questions.
Thank you for your talk.
Thanks.
How do you fit that when your model on the input output portion?
This one?
Yeah, this part.
Mm-hmm.
Also, does that model stay can you use that same model if you change? Like, I'm a little confused by the setup, because do you run some controls and then see its output and then fit a model post?
Yeah. So basically, yeah. But the robot is we control the robot by IO policies, and then this become a closed system. But it still have some input, which is the commands we given, and we can actually match the robot actual the checking performance, such as the different check how it track the different sexual working velocity, lateral working velocity, working height, something like that. And then we can actually compare the input output pairs and we can actually find the linear structure to fit this kind of data. So basically, the goal is that we use the input, and we find the parameters of this kind of linear systems, and the output, we want to minimize the output, the predicted output, and the robot actual outputs. Yeah.
So then would the use of this be like, if you want to run the same system again, like the same controls again?
No, everything will be like if you fix the same controllers, the fitting result is basically the same, because it's determined, not determined, but yeah, it's just the same. Like we run many times, and the fitting results are almost the same. Yeah, they're almost the same. Yeah. But if you change the control policies, yeah, the fitting result is different. Yeah.
Wait, when you say control policy, do you mean like state to action? So like, or do you mean like a set of a trajectory of controls, control policy?
The controller is basically the IO policy. It's just directly join output the robot actual joint positions, and with some robot observations. Yeah.
Okay.
Yeah. There's just a controllers itself. Yeah.
Mm-hmm. So like, could you do this online then, or is this all you have to do this online?
So the identification is so controller is basically online controllers. Like we need to have a real-time feedback, right? The identification is performed offline. We need to firstly collect data, because we need to know how the response looks like. So if you want to see the identification, we need to know how the response looks like, the step response, frequency response, something like that. Yeah, so this should be, we should firstly collect data and then do identifications. Yeah, I think a very interesting future work in like how can we identify it online could be interesting. Yeah.
Thank you. So online, we have a question from Hirsch. When you approach the more agile velocities where the learning controller has advantages over model-based controllers, does the linearity safety guarantee still hold?
So first of all, if you see this response, we are using the entire range of the commands, ranging from the maximum speed to the maximum forward speed to the maximum negative speed. So basically, the identifications, the linear representation is actually can describe the entire range of the physical command regions. So basically, the model is basically, we can assume that the model itself is actually good enough to describe the entire range. When even the speed is towarding the maximum range of the velocity we can control with. Yeah. So yeah, but still, I think the drawback of this method is that they still have some errors, the fitting errors. So it's not perfectly fit. So still have some error on the models, on the linear model we found. So we cannot say we actually can apply a formal safety guarantee. So but in this case we need some robust form of a CBF. But the robust form of CBF on the MPC is actually open questions. So yeah, so right now we can just say like we can just use this method because MPC can run it online very fast. So even there is some small modeling errors, we can still regulate that. Yeah.
Any other questions? What does the global planner that you use look like?
Oh, this one. This local planner is basically A star. It's just about there's go just A star to it's a collision free. Just give out a collision free, the global path.
So does it consider the dynamics of the robot, or you're just choosing some like? Yeah.
No, the global planner doesn't consider any dynamics, because if you want to do is like planning a that large range, we cannot consider dynamics. It's basically a search-based algorithm, just A star.
Yeah, A star. Okay. Mm-hmm. And then you just allow the local planner and NPC to control the robot to follow this path.
Yeah, to check the path while avoiding obstacles nearby. Yeah.
Now I see that you have a MATLAB simulator, like how do you connect that to a MATLAB simulating dynamics? Is that the dynamics model? Is it MATLAB?
Yeah, the robot, the high fidelity simulator is developed in the MATLAB. So basically, it's actually modeled very details of the robots. So this is provided by the manufacturer of the Cassie, which is Agility Robotics. Yeah. So the dynamic itself is simulated in MATLAB. Yeah.
Is it an easy thing to port it over? Like, what language do you work in? Or MATLAB too?
So it's like MATLAB is basically MATLAB. It just the MATLAB is a language, and but the vision is simulated in gazebo, which is rows, running rows. So we actually sync these two kind of these two softwares. So basically, we simulate the visions only in gazebos, and we simulate the dynamics in MATLAB. But we have a rows wrap up to communicate between cross different simulators.
Oh, okay.
Yeah.
Yeah. So ROS allows you to communicate between these different.
Yeah.
Hi, I have another question about okay. You see this, I guess, paradigm being ready for some actual task for the robot, or maybe on the Boston Dynamics spot level, or do you think there's more theory needed, like the, let's say, the robust NPC, or that more theory needs to be developed before this becomes a useful, like, universal controller for robot?
Yeah, I think they're actually very good questions. So I think the Boston Dynamics spends lots of decades, lots of efforts on this kind of this way, and they're using from their talks they're using model-based methods such as NPCs. Yeah, I think NPC can actually do lots of crazy and agile maneuvers, but it actually requires tons of tunings and lots of hands and lots of expertise and lots of failures on hardware to get everything to work. But you can see that if you use IO method, we actually don't require too much kind of tunings on the hardware to get this to work. And we're just have a couple of students doing this. Yeah. So if you want to achieve a highly dynamic motions like in the real world, probably IO probably is a little bit better. But as I mentioned, yeah, there is a drawback, and there is the theory part is that we don't know like whether it will work and whether it will not work. So yeah, I think probably we need to think about if we use IO like in the future work. If eventually in the future want to let our robot controlled by IO policy, we don't, and you can actually coexist with our human beings. Right? We don't want a robot that is no guarantee like operating besides us. We don't know when it will fail, when it will not fail, which is very critical things. So we need to actually tell like whether this kind of robot controlled by IO can actually be safely operating besides us. Yeah. So I think this in this line of research, yeah, probably need more kind of a theory development on this part. But in terms of the locomotion controls for the IO using IO reinforcement learning, I think recently we have witnessed lots of kind of good papers from research lab or actually demonstrate very good agile locomotion skills like in the real world by the IO method. Yeah.
Well, thank you.
Thanks.
Any last questions? I think that would be it, but thank you, Zhongyu, for coming to speak with us.
Thank you for the invite.
Interesting talk, and we hope to see your work in the future.
Thanks.